Hello students, Mr. Courtney here. In this video, I'm going to be going over periodic trends, talking about oxidation states, atomic and ionic sizes. But what does periodic mean? So let's start by talking about periodic. A simple definition of periodic would mean repeating. So something that repeats. And when we talk about a trend, we talk about a property also. So we're talking about a property that repeats. We're going to look at how these trends are seen on the periodic table. How does that affect the arrangement of the periodic table? And we're going to go and explain these trends as we go along. And what we're going to look at today would be oxidation states, atomic and ionic sizes. So what do all elements in a group have in common? And remember, a group goes vertical, so from top to bottom. These are our main group elements. Okay, so we're looking at our main group elements. What is it they have in common? Well, if you remember, they all have the same number of valence electrons. So those in group 1A would have 1 valence electron, 2 valence electrons in 2A, 3A, 4A, so 3 respectively, 4, 5, 6, 7, and 8. So all the elements in the same group have the same number of valence electrons. Right. Before we start talking about the trends, there are some definitions we need to know. We need to talk about core electrons, valence electrons, isoelectronic. All these we've come across already. We've discussed this already, but we're going to go and review them and make sure you remember what these are. So the core, we start off with the core electrons. Core electrons are the electrons in the lower energy levels. Okay, so there are electrons in the lower energy levels. So there'll be all the electrons except the valence electrons. So what are valence electrons? Valence electrons are the electrons in the outermost energy level. Alright, so they're the electrons in the outermost energy level. Now isoelectronic. Isoelectronic means same electron configuration. Okay, and some examples would be like if we started off with fluorine, the fluoride ion would have the same electron configuration as neon, because fluorine would have gained 1 electron. If you look at potassium, the potassium ion, it would have lost 1 electron, so it would go from 19 to 18, so it would have the same electron configuration as argon. So that's what we talked about isoelectronic, having the same electron configuration. Okay, oxidation number. Oxidation number is basically the charge. So the charge formed. Another way of saying it is the charge of the ion. Okay, so it's a charge of the ion. So whether it's a +2, -1, +3, +1, or -3, all these, that would be our oxidation states. Okay, our oxidation number. Now, when we talk about a stable configuration, we talk about this is what should come to mind, the octet rule. And what does the octet rule mean again? It means that the outermost S and P sublevels are the orbitals. The outermost P and S orbitals are filled. So we're looking at something like that would end with a S2P6 configuration. And if you remember on the periodic table, your noble gases, these here, they end with the S2P6. So they have that stable configuration. All right, so let's look at some of these examples. So we're going to start with sodium. Sodium has a configuration of, our electron configuration of 1s2, 2s2, 2p6, 3s1. So in order to form its ion, it's going to lose one electron. So it's going to lose one electron. Where does that one electron come from? It comes from our S. So we lose that one electron here. So we no longer have a 3s. So which element is, or which noble gas is it isoelectronic with? So it lost one electron. What is a noble gas before this? Before sodium, that becomes neon. So it tells us it is isoelectronic with neon. Okay. So when it loses that one electron, it becomes isoelectronic with neon, and it's going to form Na plus because it lost one electron. So now it has one more proton than electron. Now magnesium. Magnesium has the electron configuration of 1s2, 2s2, 2p6, 3s2. Now to form its ion, it's going to lose two electrons now, so it's going to form Mg, magnesium, the magnesium ion Mg plus 2. Where do these two electrons come from? Again, they're going to come from the S. And again, it's going to be isoelectronic with neon. Okay, let's look at one more. Let's look at sulfur now. Sulfur has a configuration of 1s2, 2s2, 2p6, 3s2, and 3p4. Now to form its ion, or to get a stable configuration, in this case it's going to gain two electrons. If it gains two electrons, now it's going to have two more negative than positive, so it would form the S minus 2. So now our configuration would not read end with 3p4. Instead, it will end with 3p6 because we gained two electrons. So what is that isoelectronic with now? Okay, so it is isoelectronic with argon. Okay, so that's how you do that. Again, we're just looking for finding the stable configuration, the octet rule. 8 valence electrons, 2 in the S and 2 in the P, in the outermost S and the outermost P. And we also have to remember here that positively charged ions are called cations, and negatively charged ions are called anions. Okay, so positively charged ions are called cations. These ones are called anions because they're negatively charged. Now the charge on the main group elements. Main group elements have a charge based on the number of electrons they gain or lose. Group 1 would lose 1, so they're going to have plus 1. These are going to lose 2, so it's plus 2. Lose 3, plus 3. These here could gain or lose, so that's why it's positive or negative 4. These will gain 3, so it's negative. Gain 2, negative. Gain 1, negative. And these will neither gain nor lose, so their charge will be 0. So based on what we've seen here, what determines the charge of the main group elements? Again, it is determined by their valence electrons, the number of valence electrons. How many electrons do they have to gain or lose to gain that stable configuration with the S2 and the P6? So what about the charge of transition metals? Transition metals, as we see here, they do not form a set of one charge or one set of charge. So you can see iron has 2, cobalt, nickel, coppers. They have multiple charges that they can form. What is responsible for that? Let us look at iron as an example. Iron would have the configuration of AR. Let's change the color. So we're going to write the noble gas configuration 4s2 3d6. Now to form the first ion of iron, which is the +2, we're going to lose our s2 electrons. Okay, so here it loses 2 electrons to form Fe +2. Okay, so it loses those 2 electrons. Now we can also lose a 3rd electron. So it's going to lose one from here, from the D. D now becomes 5. So you can lose 3 electrons to form the ion 3. When it loses the 3 electrons, it forms the, as we said, the 3d5. Remember that the half-filled D is more stable. All right, so we have to remember that the half-filled D is more stable. So these are the ions that it can form. Copper. So why does copper form a +1 charge? Remember, copper is one of those we talked about being the exceptions to the filling rules. Copper would have the configuration AR 4s1 3d10. So remember, it moves 1 electron from the 4s into the 3d to fill that 3d, because the 3d, or a full D, is more stable. So when it loses that electron, when it has to form an ion, it would lose this 1 electron just to leave us with a 3d10. That's how it forms the +1, and it's an exception. Or if it forms the +2, what would happen in the +2? It would be 4s2 3d9. These 2 electrons would lose to give us that would give us copper +2, and this one would give us copper +. So now let us get into the factors affecting periodic trends. So distance from the nucleus. As energy level increases, the electrons are further away from the nucleus. So let's say this is our nucleus. And we're going to just draw energy levels. So as you see, as we add more energy levels, the distance from the center to the electrons increases. So if we compare these, all these will have different distances. So they're further apart. So the nucleus, which is positively charged, has less effect on the electrons in the outer energy levels. When we talk about, now we also talk about the effective nuclear charge, and we call that the Zeff. That's the difference between the number of protons and electrons. So to calculate Zeff, we'll look at the atomic number, the number of protons, minus our core electrons, which is essentially the same as the number of valence electrons. And we'll talk about that later on also. Shielding effect. Here, the core electrons act as a barrier to the valence electrons. So the valence electrons are shielded from the nuclear pull. That is the pull of the protons in the nucleus. So let's look at this. So if this is our nucleus, we have our first set of electrons here. Now our electrons will be attracted, these 2 electrons would be attracted to the nucleus, or the nucleus will have a strong pull. But as we go out, if we add another energy level, the electrons here will be shielded by these 2 first. And if we add another energy level, the pull of the nucleus has to be shared between these three energy levels. So it would have a stronger pull on those closest to it. So it would have a stronger pull on those in the first energy level, then in the second. And as you get out to the outermost, or the valence electrons, the pull of the nucleus will be far less. Electron repulsion. Remember, electrons are negatively charged. So as we add electrons, the electrons tend to want to move further away from each other. So they don't want to stay there. They're going to want to move further apart. So in other words, as we add more electrons, what's going to happen is that they want to move further apart. So they're going to pull. That's what we call push, or they repel each other. So as the electron repulsion, because the electrons want to repel each other, because we keep adding them to the same energy level. Okay, so if I'm adding electrons here, I can add. So as I add electrons, I'm adding to the same energy level. And these electrons want to be as far apart as possible. And the only way they can be as far apart as possible is by pushing away or repelling each other. And you have to remember that they have the same charge. So that is going to help them push. That's why they're going to repel each other. So let's talk about the first trend, atomic size. So when we talk about atomic size, we're looking firstly in the group. So we're looking as we go down the group. Okay, so we're looking at atomic size as we go down the group. Let's look at the different factors that would affect it. First of all, the distance from the nucleus will have an effect on it. Because as we go down, what do? We increase energy level. So as we go down, we increase energy levels. If we increase energy levels, therefore, size increases. Okay, and you can always see that in add energy levels, the size will increase. And then we look at the shielding effect. The core electrons are going to shield the valence electrons from the nuclear pull. So the core electrons shield the valence electrons from the nuclear pull. All right. So they shield them from the pull. Now, effective nuclear charge and electron repulsion does not play a role in the size of this. So generally, we see here as we go down the group, atomic size will increase. And it increases because the distance from the nucleus increases and because of shielding effect. So atomic size in terms of a period as we go left to right. Now the distance from the nucleus does not change because we're in the same energy level. So that does not change. Now the effective nuclear charge is going to be higher. Now why is the effective nuclear charge higher? We have more electrons added to the same energy level. So if we add more electrons at the same energy level, we're not shielding them, but we're increasing the number of protons, so there's going to be this means therefore stronger pull. So the protons will have a stronger pull on the electrons, meaning that the atom will be, which is going to equal to a smaller atom. So here we see as we go left to right, the size of the atom decreases. All right. Let us summarize this. Atomic radius, that is the distance from the nucleus to the outermost energy level. in a neutral atom. And as we can see here, we just talked about this. As we go down the group, atomic size increases, or atomic radius increases. As we go across the period left to right, the general trend is for atomic radius or atomic size to decrease. Now it's important, one of the things you can learn is that cesium has the largest atomic radius. And as you move away from cesium, atomic radius is going to decrease. So if you go into the right, away from cesium, or you're going up away from cesium, it's going to decrease. If you're going to the left, towards cesium, or down towards cesium, atomic size is going to increase. So that is something you can use to help you think about atomic radius or the size of atoms themselves. Okay, so let's look at calculation of Zeff. Remember, the Zeff, or effective nuclear charge, is equal to Z, or atomic number of protons, minus the core electrons, the number of core electrons we have. So for beryllium has 4 protons and 2 core electrons, so that gives us 2. Carbon would have an atomic number of 6 with 2 core electrons, so that gives us an effective nuclear charge of 4. Nitrogen, an atomic number of 7 with 2 core electrons, so that gives us a Zeff of 4. Fluorine, that'd be 9 core electrons minus 2. Sorry, not 9 core, but 9 protons minus 2 core electrons, so that gives us 7. Now you can see a trend here. Now you also may be wondering, where do we get this 2 from? Quickly, if you remember, all these elements are in which period on the periodic table? So see if you can find them quickly. They're in period 2. So that means that core electrons would all be, so they would all have the same core electrons of 1s2. So that this here is the core electrons that they have. What do you see as we go from beryllium across to fluorine? The effective nuclear charge increases. And as we said before, effective nuclear charge is same as the number of valence electrons. Again, look at where beryllium is. Beryllium has 2 valence electrons. Carbon has 4. Nitrogen 5. And fluorine 7. So let's look at some for transition elements. So titanium and vanadium. Titanium has a configuration of argon 4s2 3d2. Okay? And its atomic number is 22, so if we calculate in Zeff, that'd be 22 minus 20, because we have 20 core electrons, because this here is our valence electron, so this will be factored into our core electron. So 20 minus 22, that gives us, so 22 minus 20, so that gives us 2. Now vanadium, for S2 3d3. So its atomic number is 23, but it has 21 core electrons. So that gives us an effective nuclear charge of 2. So what do we see here? So for D block, so for our D block elements, the size is constant, or relatively constant, so the size does not really change here. So now we're going to compare the size of ions. We're going to look at cations, so that is when they have a positive charge to cations, or anions to anions, that's when they have negative charge. So when they gain, or when they lose rather, to form their cations, or gain to form their anions. Remember, as we go down the group, what happens to the charge? What happens to the size? It increases. So in the ions, as we go down the group, the size of they will also increase. So that means it's going to increase due to energy level. because we keep adding energy levels as we go down. Same thing for our anions. Okay, so they're going to increase due to energy levels. Or should I say due to additional energy levels? Yeah. Yeah, so they increase due to additional energy levels because as we go down, we keep adding energy levels. Now, what happens as we go left to right? Or right to left. As we go right to left, we're going to have, and that's not what I want to do. Okay, we're going to have a smaller effective nuclear charge because we're decreasing the number of electrons, keeping the number of protons the same. So we're going to decrease the Zeff. If we decrease the Zeff, so we're going to have a smaller, so the size is going to decrease here. Sorry, not decrease. If we have a smaller Zeff, then the size is going to increase. All right. So smaller Zeff, size is going to increase because as we go, we already know as we go from left to right, the size decreases. So that means if we go right to left, the size is going to increase. So now let's compare cations to anions. So if I'm going to use this representation here, we have our nucleus and we have our energy levels. If we're going to form a cation, that means we're going to lose electrons. If we lose electrons, we lose an energy level. So what happens to the size? The size decreases. Whereas when we have our anions, we just add electrons to this outer energy level. Okay, so in the same period, as we go in this direction, in the same period, anions will be larger, than cations. And the cations are smaller because they have lost an energy level. So we know that cations are going to be smaller. And all this is in the same energy level. So as we go left to right, we can see that. So they're going to be smaller due to loss of energy levels. Again, so when we form cations, they're going to lose electrons. When they lose electrons, they lose an energy level. Again, so when they lose an energy level, so this energy level here is going to be lost. So that's why they get smaller. But when they form anions, they just add electrons to this energy level. So the energy level does not change. The number of energy levels does not change. And here we can see what ionic radius is now. Ionic radius is similar to atomic radius, except it's the distance from the nucleus to the outermost energy level in an ion. So that's after it's lost or gained electrons. And here we can see, look at lithium, 152 picometers. That's the lithium atom. The lithium ion is 60. So you see it decreases. Look at fluorine, the fluoride ion. Fluorine is 64 picometers. But the fluoride ion is larger. So we just talked about this. Cations are smaller than anions in the same energy level. So if you can look, you will see that. Same thing down here. Look at sodium compared to chlorine. So if we compare the size of ions to their parent atoms or their neutral parent atoms, if we look at calcium and the calcium ion, so calcium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, to form its ion, it's going to lose 2 electrons. So if it loses 2 electrons, it's going to lose from here. So it loses the 4s2. Notice we've lost an energy level. So calcium ion will be smaller than the neutral atom. So here we can see cations are smaller than neutral atoms because they have what? What do you think it is? They have one less energy level. Remember, because they've lost an energy level. All right, let's look at fluorine and fluoride. Fluorine has an electron configuration of 1s2, 2s2, 2p5. So that's fluorine. Now, fluorine has to gain one electron to form its ion to get that stable configuration. So it gains one electron. Now it becomes 2p6. So we have not lost an energy level. What we've done is we've added an electron to the same energy level. Remember, we talked about when we add electrons in close proximity, they tend to push or they tend to repel each other. They're not going to attract, but they want to move away from each other. So that's going to increase the size. So anions are larger or bigger than neutral atoms because electron repulsion cause the electrons to spread out because they want to be as far apart as possible from each other. So let's use what we've just learned to answer this question here. We're going to compare the sizes of the magnesium ion to oxide ion and to the neon atom. Now, let's look at these in terms of the number of protons first. Magnesium ion, or magnesium, would have 12 protons. Okay, so that's protons, P plus. The oxide would have 8, because that's oxygen's atomic number. And neon, okay, right in the wrong place, neon would be 10. Okay, so that's the number of protons. Now, look at the electron configuration. The magnesium ion would be 1s2, 2s2, 2p6. And if you look at oxygen also, it gained 2 electrons. So it would have the same configuration. Neon has the same configuration. So the two ions are isoelectronic, meaning that they have the same electron configuration as neon. But what is different? We said that they have the different number of protons, but they still have the same number of electrons. So since they have the same number of electrons, that means there's going to be a greater number of protons. The one with the greater, so the greater number of protons equal a stronger pull. So if we have a stronger pull, what's going to happen? So that means magnesium ion will be smaller than the neon, which is even smaller than the oxygen ion, because most proton, least proton. So we have the greatest pull here, weakest pull here, because we have more protons, less protons here. So if we're going to compare the size of these three ions, first of all, we need to look at their electron configuration. So potassium, oxide, and iodine. So we're going to write the electron configuration. Neon, 3s2, 3p6, because it lost one electron. 1s2, 2s2, 2p6, because it gained 2 electrons. And iodine would have gained 1 electron, so it's going to be 5s2, 4d10, 5p6. So how are we going to compare these? We have to look at their energy levels. Because before we talked about as we added energy levels, what happened again? What happened to the size of the atom as we added energy levels, or the size of the ion? Yes, you're correct. It increases. So if we increase, so we look at the energy levels. The one with the smallest number or number of energy levels will be the smallest. That's our oxide. So it will be smaller than our potassium ion, which is smaller than our iodide ion, based on the number of energy levels. So we went from fewest to most. And that's in terms of energy level. So this takes us to the end of this lesson. So you can, as usual, pause the video wherever you felt like it. You review it as many times as you want to, but you need to have this covered for our class. We're going to discuss it, take your questions, and then we'll look at some problems in class. So until the next time, I'm out. Blessings.